is also pretty cool. It tells us about the wave model of light, and then a lot about the model of the different models of the atom, um, and the photoelectric effect, which is also really cool. So, when we're working with quantum theory, we get into a number of different topics, which firstly involve Young's double slit experiment. You may have heard of that already, just kind of as general knowledge, and the wave model of light. So, the tricky thing with Young's double slit experiment and the black body radiation. These two differing experiments done kind of in the late 1800s and early 1900s, which kind of provide evidence both that light can act as a wave, but light can also act as just a discrete particle. So, basically, we have evidence from Young's double slit experiment that light is wave, but we have evidence from black body radiation and also from the photoelectric effect, which was another experiment done even later than that in the 1900s, which show that light is a particle. So Einstein basically came up with this theory, which describes light as being both a wave and a particle. So we're then going to investigate the dual wave particle nature of electromagnetic radiation. We're then going to solve problems involving the photoelectric effect, and then describe the Bohr and Rutherford model of the atom, and how it integrates light quanta and atomic energy states to explain wavelengths observed in the hydrogen emission spectra. So, getting into Young's experiment. So, Young's double slit experiment was performed in the early 19th century by Thomas Young, and it helped to prove the wave model of light. So, how it did that is it showed the presence of interference patterns, proving that light acts as a wave. So, what Young observed was that if he kind of had a piece of screen with two slits and he shone light through the screen, he would see a destructive and constructive interference pattern, which basically you would have learnt about previously in year 11 with waves, which is where like the two positive parts of a wave will collide and create an even bigger positive part, or the two negative parts will collide, or alternatively two kind of opposing parts, either a positive displacement and negative displacement will collide to kind of cancel out. So this is kind of, I'll draw actually more of a diagram because it'll be more helpful to what he saw. So basically what he saw, the pattern that he saw was kind of a big pattern of light, two big patterns of light with kind of petering out sections on either side, which describes like an interference pattern of waves. As we can see in the next slide, what he would have seen if light acted solely as a particle was this like evenly distributed um, evenly distributed patches of particles. So this in this experiment, we're just seeing electrons, which are obviously particles. Um, so what he saw with light was these kind of like this uneven um, pattern where we have all of these different um, like splotches of light, which kind of implies that when the light goes through the slits, it bends around the slit and creates these patterns. However, if light was a particle, the particles would have just gone through these two slits and created like two big splotches of particles right on either sides of the splits. So this is how he knew that light could act as a wave. Okay, now we are getting onto the Bohr model. So the Bohr model of the atom is probably the one that you guys are most familiar with. It's a model of the atom where negative electrons orbit in discrete energy levels around a positively charged nucleus. So we have the protons and the neutrons in the nucleus, and then the electrons orbiting around. An important feature of the Bohr model is that the electrons can only exist in discrete energy states. So the electrons are going to have a certain amount of kinetic energy, and the orbital ring that the electron is going to be in depends on that energy. So if it has more energy, then it's going to be closer to the outside of the atom, but if it has less energy, then it's going to be closer to the inside. However, an electron cannot be in between energy states, right? It can never be on 1.5. It can either be on one or the other. It can never be in between. Okay. Photons incident on atoms can cause electrons to go up in energy levels into causing anti-bonding orbitals. So what this means is that if a photon, which is a particle of light, interacts with an atom, it's going to give the atom all of its energy. And as a result, some of the electrons are thus going to have all this extra energy and jump out of the atom. When the electrons fall back down to lower energy levels closer to the nucleus, then a photon of equal energy is going to be emitted. This model proves that light can also act in discrete quantity, photons. The energy of the photon is going to match the difference in between energy of the orbitals. And we can calculate the energy using Planck's equation, which is what we have here. Change in energy is going to be H